Welcome to the Wonder Lab. Tonight we embark on a journey into the strange, mesmerizing world of quantum reality, a place where our everyday intuitions collapse. Probabilities, and information itself behaves in ways that defy classical understanding. From entangled photons whispering across kilometers of fiber, to quantum states that vanish and reappear without traveling through space. This is the frontier where physics becomes not just a science, but a philosophy of connection, uncertainty, and possibility. In this journey, we will explore the invisible threads of the quantum universe, the laws that govern the smallest constituents of matter, the phenomena that make unbreakable communication possible, and the mysteries that challenge even the greatest minds of our time. Here, the uncertainty principle is not a limitation, it is a guardian. The randomness that puzzled Einstein now protects secrets, enables teleportation of information, and inspires visions of a quantum internet. Join us as we uncover the principles behind quantum key distribution, the magic of teleporting quantum states, and the subtle, elegant laws that turn fragility into strength. From cities building secure quantum networks to satellites beaming entangled particles through the sky, the boundary between science fiction and reality blurs. Every photon, every qubit, every flicker of probability tells a story, one that connects distant parts of the universe in ways that classical science could never imagine. The Wonder Lab invites you to witness this extraordinary tapestry of reality, where observation shapes existence, measurement writes history, and information flows not just as data, but as a bridge between worlds. In tonight's exploration, we'll not only observe quantum phenomena, we'll feel their implications, understand their significance, and marvel at the poetry hidden in the mathematics of the universe. So sit back, breathe, and prepare to let your curiosity wander into a dimension where certainty fades and possibility reigns. This is the Wonder Lab. Welcome to the quantum journey. The world we experience every day feels solid, predictable, and continuous. Objects sit in one place, time flows steadily, and cause and effect govern every interaction. Yet, beneath this comforting veneer, lies a realm where certainty evaporates and the very fabric of reality dances to a rhythm we can barely comprehend. Welcome to the quantum world, a dimension where particles exist in multiple states simultaneously, where observation shapes outcomes, and where information itself becomes a physical entity, inseparable from the systems it describes. In this realm, photons can be entangled across kilometers. Electrons can tunnel through barriers without ever crossing them. And probabilities, not certainties, dictate every event. These are not abstract curiosities confined to textbooks. They are phenomena being harnessed in laboratories, networks, and satellites, shaping the future of communication, computation, and understanding itself. Our journey begins with the fundamental concept of superposition. Imagine a particle existing in two places at once, or spinning clockwise and counterclockwise simultaneously. This is not metaphor. It is the strict prediction of quantum theory, verified countless times through precise experiments. But how do we reconcile this with the classical world we see? That bridge between the microscopic and macroscopic, between the strange and the familiar, is where quantum mechanics teaches us humility. The universe is far more nuanced than our senses reveal, and in understanding it, we are forced to reconsider what it means to measure, to observe, and to know. As we delve deeper, we will witness how these seemingly fragile phenomena give rise to some of the most secure forms of communication ever imagined, and how the probabilistic nature of quantum mechanics becomes not a hindrance, but a tool, a means to encode, protect, and transmit information with unparalleled precision. From the flicker of a single photon to the vast entanglement across continents, the quantum world challenges us to think differently, to embrace uncertainty, and to marvel at the intricate tapestry woven by the laws of nature. In the quiet glow of a laboratory, a single photon begins a journey that would be impossible to intercept, impossible to copy, impossible to erase without leaving a trace. This is the promise of quantum communication, a field that transforms the peculiarities of quantum mechanics into the most secure form of information transfer humanity has ever conceived. Unlike classical encryption, which relies on complex algorithms and the presumed difficulty of certain mathematical problems, quantum communication relies on nature itself to enforce secrecy. At the heart of this field lies quantum key distribution, or QKD. In classical cryptography, a secret key, just a string of random numbers, is shared between two parties to encrypt messages. The security of that key depends on its secrecy during transmission, which is always vulnerable. But in QKD, the key is encoded into quantum states, typically using photons with specific polarizations. The laws of physics then act as guardians. Any attempt to measure or intercept these photons inevitably alters them, producing detectable disturbances. The sender and receiver can compare a subset of their data. If anomalies exceed the expected noise, they immediately know an eavesdropper is present. This isn't about computational power or clever hacking. It's about fundamental physical laws. Even a quantum computer, operating at the edge of what is possible, cannot break this kind of security without leaving fingerprints. The uncertainty principle itself becomes a sentinel. The more you try to extract information, the more you betray your presence. Over the last few decades, QKD has evolved from theory into practice. Cities like Vienna, Beijing, and Geneva have implemented quantum-secured networks spanning tens, even hundreds, of kilometers. In 2017, China launched a satellite capable of transmitting entangled photons between ground stations thousands of kilometers apart, forming a secure quantum link through space. These milestones are steps toward the long-anticipated quantum internet, a network that not only encrypts messages with unbreakable security, but also allows synchronized operations, distributed computation, and communication that respects the principles of nature rather than attempting to circumvent them. Beyond security lies the concept of quantum teleportation, a process that defies intuition yet remains grounded in rigorous mathematics and experiment. Teleportation, in the quantum sense, doesn't move matter. Instead, it transfers the state of a particle from one location to another, reconstructing it perfectly elsewhere while leaving the original particle behind. Through entanglement, measurement, and classical communication, the information defining a particle state is transmitted, preserved, and reconstituted. It's a delicate choreography of randomness, precision, and correlation, a dance that stretches across space without violating the speed of light. Randomness plays a critical role throughout. Classical random number generators are never truly random. They are pseudo-random, predictable if one understands the underlying algorithm or physical process. Quantum systems, by contrast, produce intrinsic randomness. When a photon encounters a polarizing beam splitter, its path is fundamentally unpredictable, determined not by hidden variables, but by the laws of the universe. This randomness is now harnessed in quantum random number generators, feeding encryption, scientific simulation, and gaming applications, providing unpredictability that no adversary can anticipate, yet. Even as quantum communication matures, challenges remain. Entanglement and quantum states are fragile, sensitive to noise and loss. Unlike classical signals, quantum information cannot be amplified without disruption. Long-distance communication requires quantum repeaters, devices that extend entanglement segment by segment, connecting nodes through operations like entanglement swapping while preserving coherence. These devices, though slow and technically demanding, are the linchpin for scaling quantum networks to global dimensions, allowing secure communication across continents, linking satellites, ground stations, and city networks in a coherent lattice of entanglement. Every limitation becomes a safeguard. The impossibility of copying quantum information ensures security. The unpredictability of measurement guarantees true randomness. The fragility of entanglement enforces careful design. In embracing the very principles that once seemed obstacles, we create networks that operate in harmony with nature. Quantum communication is not just about secrecy. It is a profound reimagining of what information is, how it exists, and how it moves. It reminds us that in the quantum realm, data is inseparable from the systems that carry it. That information is not an abstract commodity, but a tangible, physical entity woven into the fabric of reality itself. As photons travel, entangle, and teleport, as keys remain unbroken and information flows unseen, one fundamental question persists. What does it all mean? Quantum mechanics works with astonishing precision. It predicts lasers, explains atomic structure, guides GPS satellites, and powers the technologies of our modern world. Yet, when we step back from the equations, the universe presents us with a puzzle that refuses to dissolve. The formalism tells us what will happen when we measure, but it remains silent on what exists when we are not looking. Throughout the 20th century, physicists and philosophers have offered various interpretations to bridge this gap. Each interpretation is a story, a lens through which we try to understand the same mathematical landscape. In the early days, the Copenhagen interpretation, shaped by Niels Bohr and Werner Heisenberg, dominated thought. According to Bohr, quantum mechanics does not describe an independent reality. It describes our interface with nature, the outcomes we can measure, the probabilities that guide our expectations. The wave function, that elegant object encoding all possible states of a particle, is not a physical wave, but a catalog of potentialities. When a measurement occurs, one possibility actualizes and the wave function collapses to reflect that reality. This pragmatic view captivated many, for the predictions worked. Yet it left a gnawing discomfort for thinkers like Einstein, who famously asked, "Do you really believe the moon is not there when you are not looking at it?" Einstein's unease sparked alternative interpretations, each seeking to reconcile the mathematical power of quantum mechanics with a coherent picture of reality. One of the boldest proposals came from Hugh Everett in 1957, the many worlds interpretation. Everett rejected the collapse postulate entirely. In his view, the wave function never collapses. It simply evolves. Each quantum measurement branches the universe, creating parallel worlds for every possible outcome. In one world, a photon travels left. In another, right. Schrödinger's cat is both alive and dead, but each possibility unfolds in a separate branch. We perceive only one branch because our own state becomes entangled with that outcome, but all others exist just as real. Randomness disappears. What seems like chance is merely our position within a multiverse. It is a vision both awe-inspiring and unsettling, suggesting that the universe is vastly more complex than our everyday experience hints. Then there is the pilot wave theory, or de Broglie-Bohm interpretation, which envisions particles always possessing definite positions guided by a hidden wave. This wave, evolving according to Schrödinger's equation, steers particles along deterministic paths that appear random only because we lack full information. In this picture, uncertainty stems not from nature itself, but from our ignorance. The observer's role is clarified. We uncover pre-existing properties, guided by a non-local wave capable of influencing distant particles instantaneously, a subtle nod to the spooky action at a distance that so troubled Einstein. Other interpretations shift focus from objects to information. Quantum Bayesianism, or QBism, treats the wave function not as an external reality, but as a reflection of an observer's beliefs about potential outcomes. Measurement is personal, outcomes are experiences, and probabilities are tools to navigate uncertainty. Here, quantum mechanics becomes less a map of the cosmos and more a user's manual, guiding decisions in a fundamentally unpredictable world. There are countless other perspectives. Objective collapse models propose physical mechanisms to reduce possibilities into one reality. Relational interpretations see quantum states as existing only between interacting systems. Information-based views even consider the universe as a vast quantum computation. Each answers the same questions differently. What is the wave function? When, if ever, does possibility collapse into actuality? Yet astonishingly, the predictions remain the same. Whether we envision parallel universes, hidden guiding waves, or subjective beliefs, the experimental outcomes, the dance of photons, electrons, and atoms, are identical. The mathematics is indifferent to our stories. We can choose our lens, our narrative, but the behavior of the universe is unwavering. This unity amid interpretive diversity is humbling. It teaches that the truth may exceed any single story, that the equations are reliable, precise, and unyielding, while the meaning we ascribe is a reflection of human curiosity, imagination, and perspective. In embracing this ambiguity, quantum mechanics offers not certainty, but a graceful dance with mystery. Each interpretation is a mirror revealing our own desires for order, our tolerance for ambiguity, and our comfort with infinity. The universe provides rhythms and probabilities. It is our choice how to understand them, to weave them into coherent stories, to live alongside the questions it poses. The quantum world whispers that understanding is not about possession, but participation, that observing is an act of gentle creation, bringing one version of reality into focus while countless others remain unseen yet possible. As we step beyond interpretations and ponder reality itself, the quantum world begins to reveal applications that reshape our daily lives. Quantum communication transforms the abstract strangeness of particles into a practical, unbreakable method of sharing information. Unlike classical encryption that relies on computational difficulty, quantum communication leverages the laws of physics themselves. Here, security is not clever code, but a consequence of nature. Attempt to eavesdrop and you leave a trace. Attempt to copy and the universe itself rebels. One cornerstone of this revolution is quantum key distribution, or QKD. Imagine two parties wishing to share a secret key, a string of bits used to encrypt messages. The weak link in classical cryptography is key distribution. QKD overcomes this by encoding keys in quantum states, often using photons polarized in different directions. Quantum mechanics ensures that any interception or measurement disturbs the system, altering the photons in a detectable way. The sender and receiver can then compare samples to check for tampering. If the error rate exceeds random noise, eavesdropping is confirmed. Even a quantum computer cannot break this security undetected. The uncertainty principle itself becomes a vigilant guardian. The more you probe, the more obvious your intrusion. This system is no longer a thought experiment. Cities like Beijing, Vienna, and Geneva have demonstrated quantum-secure networks sending keys over tens or hundreds of kilometers of fiber. China's Misha satellite in 2017 beamed entangled photons between ground stations thousands of kilometers apart, creating a secure quantum link through space. These experiments mark the first steps toward a quantum internet, a network where entanglement is not only for encryption, but for communication, synchronization, and computation. Perhaps the most mind-bending aspect is quantum teleportation. Despite its science fiction name, teleportation does not move matter. Instead, it transfers the state of a particle from one location to another without moving the particle itself. This begins with an entangled pair of particles, A and B. A remains with the sender, B travels to the receiver. The sender performs a joint measurement on A and another system whose state is to be transmitted. The measurement destroys the original state but produces classical data. Sending this data allows the receiver to transform B into an exact replica of the original state. The quantum information is teleported, perfectly reconstructed, with no faster-than-light signaling or cloning. Countless experiments from tabletop setups to satellites demonstrate this process. Teleportation promises distributed quantum computing, where distant computers share states instantaneously, and secure networks, where information exists only in fleeting, untouchable forms. Randomness lies at the heart of both QKD and teleportation. True randomness is hard to achieve in classical systems. Quantum systems provide it intrinsically. A photon passing through a polarizing beam splitter has a 50-50 chance of being transmitted or reflected, fundamentally unpredictable. Quantum random number generators now serve encryption, gaming, and scientific simulations, producing sequences of bits that no adversary can foresee. Every coin flip, every photon, is a universe of chance. Yet, even the power of quantum communication faces a challenge: distance. Quantum states are fragile, easily disrupted by noise and loss. Classical signals can be amplified, but quantum signals cannot, as amplification would destroy information. Enter quantum repeaters, devices that extend entanglement across long networks. They create entangled pairs across short segments, then perform entanglement swapping to connect them. Quantum memory stores particles briefly while synchronizing with others, relaying entanglement without measurement. Though slow and technically demanding, this method is essential for scaling networks beyond cities into global reach. Researchers envision a future where quantum repeaters, satellites, and ground stations form a worldwide lattice of entanglement, a backbone for secure communication, distributed computing, and ultra-high precision timekeeping. The beauty lies in turning perceived weaknesses into strengths. The fragility of quantum states protects information. The unpredictability ensures true randomness. And the rules of entanglement create networks that respect nature instead of defying it. Each limitation becomes a safeguard, each constraint a feature. Quantum communication reshapes not only technology, but our understanding of information itself. In classical physics, information is a copyable, storable commodity. In quantum physics, information is inseparable from the system carrying it. Communicating via quantum states is not sending messages. It is extending correlations across the universe, weaving space itself with shared probability. In practice, quantum-secure systems are tested in banking, defense, and satellites. Quantum random number generators find homes in smartphones and cybersecurity chips. These silent, pervasive technologies are quietly redefining digital trust, showing how deeply quantum mechanics is entering our modern life. As quantum communication reshapes technology, The deeper mysteries of quantum mechanics continue to challenge our understanding of reality itself. While the mathematics of quantum theory predicts outcomes with unmatched precision, it leaves an enormous question unanswered. What does it say about the world when we are not observing it? The wave function, that elegant mathematical object encoding all possible states of a particle, collapses upon measurement. But why? What happens in the meantime? The earliest and most influential interpretation, the Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg in the 1920s, posits that quantum mechanics does not describe an objective reality independent of observation. It describes the outcomes of measurements, the interface between observer and system. The wave function is a catalog of possibilities. When measured, one possibility becomes real. Bohr argued that asking what happens inside an atom when we are not measuring it is meaningless. Quantum mechanics tells us what we can say about nature, not what nature is. Many physicists accepted this modest stance, valuing predictive power over metaphysical certainty. Yet, not everyone was satisfied. Einstein famously resisted the idea that the moon does not exist when unobserved. For those uneasy with observer-dependent reality, other interpretations emerged. One of the most striking is the many worlds interpretation proposed by Hugh Everett in 1957. Everett took the wave function literally, rejecting collapse as a separate rule. In his view, all possible outcomes occur simultaneously, each in its own branch of reality. The universe continuously splits, creating parallel worlds for every quantum event. In one world, a particle lands left. In another, right? Schrödinger's cat lives in one, dies in another. From our perspective, only one branch is visible, yet all exist equally. Many worlds eliminates randomness. The wave function evolves deterministically everywhere. What we perceive as chance is our position in a branching multiverse. Some physicists find it compelling. Others see it as extravagant. Another alternative is the pilot wave theory, or de Broglie-Bohm interpretation. Here, particles have definite positions guided by a hidden wave evolving according to Schrödinger's equation. Apparent randomness arises not from indeterminacy, but from ignorance. The observer uncovers part of a pre-existing reality, though intuitive. This approach requires a non-local guiding wave capable of influencing particles instantly across vast distances, spooky action at a distance that even Einstein would have grimaced at. Beyond these, interpretations such as QBism, quantum Bayesianism, emphasize the observer's beliefs and personal experiences. The wave function is not a description of an external reality, but a tool for making rational decisions in an uncertain world. Measurement outcomes are subjective experiences rather than objective facts. This perspective turns quantum mechanics into a user manual for navigating uncertainty. Other interpretations include objective collapse models, where the wave function physically collapses due to mechanisms built into nature. Relational interpretations, where quantum states exist only between interacting systems, and information-based views, which treat the universe itself as a quantum computer. Each interpretation addresses the same core question differently. What does the wave function represent, and when does a probability become reality? Remarkably, no matter which interpretation one chooses, the predictions of quantum mechanics remain identical. Electrons, photons, and atoms behave exactly the same. The equations do not care which story we tell, they simply work. In this sense, quantum mechanics is like a language we fluently speak without fully understanding the poetry behind it. Its unity amid philosophical disagreement is both humbling and liberating. It shows that reality might be deeper than any single narrative can capture. The mathematics provides rhythm, Meaning is what we derive from it. Quantum mechanics offers mystery shaped by precision. Each interpretation is a mirror reflecting different aspects of human understanding, our desire for order, tolerance for ambiguity, and acceptance of infinity. The equations remain constant, the outcomes predictable, but the stories they inspire are endless. Understanding is not merely finding answers. It is learning to live gracefully with questions. In a universe layered with possibilities, perhaps the truest interpretation is the simplest. All stories coexist simultaneously, and each observer gently brings one version into focus. As we explore these interpretations, we begin to see that quantum communication, teleportation, and randomness are not just technological curiosities. They are expressions of a deeper reality, one that challenges our classical intuitions and redefines the boundaries between information, observation, and existence. As we leave the philosophical debates behind, we return to the astonishing practical implications of quantum mechanics, its application in communication, and the security of information. Classical cryptography relies on algorithms and computational difficulty, but quantum communication rewrites the rules entirely, relying on the laws of physics themselves. Here, security is not an abstract promise. It is physically enforced. Any attempt to eavesdrop leaves a detectable trace. Quantum key distribution, QKD, is one of the simplest yet most profound tools in this new world. In traditional cryptography, sharing a secret key safely is always a vulnerability. QKD encodes keys into quantum states, usually photons with varying polarizations. Due to the peculiar nature of measurement in quantum mechanics, any interception disturbs the photons. By comparing portions of their data, sender and receiver can detect tampering. The security does not depend on the complexity of mathematics, but on the inviolable laws of nature. Even the most powerful quantum computer cannot break it without detection. QKD turns Heisenberg's uncertainty principle into a vigilant guardian. The act of observation reveals itself. Over the past decades, quantum networks have moved from theory into reality. Cities like Beijing, Vienna, and Geneva now demonstrate quantum-secure networks spanning tens to hundreds of kilometers. China's 2017 satellite experiment sent entangled photons across thousands of kilometers, proving that secure communication can extend into space. These networks are the early steps toward the quantum internet, a network leveraging entanglement not just for encryption, but for communication, synchronization, and computation. Another mind-bending concept is quantum teleportation, not of matter, but of quantum states. A particle's state is transferred from one location to another without moving the particle itself. Starting with a pair of entangled particles, one stays with the sender, the other goes to the receiver. A joint measurement on the sender's particle and the state to be transmitted produces classical data. This data sent conventionally allows the receiver to reconstruct the exact quantum state on their particle. Teleportation thus moves quantum information without any physical transfer, preserving security and enabling future distributed quantum computing. Central to both quantum cryptography and teleportation is randomness. True randomness is elusive in classical systems, which rely on pseudo-random algorithms. Quantum mechanics, however, provides fundamentally unpredictable outcomes. A photon passing through a polarizing beam splitter has a 50-50 chance of being transmitted or reflected, with no hidden variable determining the result. Quantum random number generators now power encryption, gaming, and scientific simulations. In a digital age where predictability is vulnerability, these generators create sequences that no adversary can foresee, producing information born from the very indeterminacy of the universe, Yet challenges remain. Quantum states are fragile. Unlike classical signals, which can be amplified, quantum information cannot be copied without destruction. Distance remains a formidable barrier. Enter the quantum repeater, a device that extends entanglement step by step across long networks. Entangled pairs are generated over short segments, then connected through entanglement swapping. Each node temporarily stores entangled particles in quantum memory, relaying coherence without direct measurement or amplification. Though technically demanding and slow, quantum repeaters are the key to global quantum networks. The vision is a world where satellites, repeaters, and ground stations form a lattice of entanglement. Secure global communication, distributed quantum computing, and ultra-high precision timing all become possible. The fragility of quantum states and unpredictability of measurement are no longer limitations, they are features. Every restriction becomes a safeguard. You cannot copy a quantum state undetected. You cannot predict outcomes in advance. You cannot amplify entanglement without disturbance. Networks are built respecting the laws of nature rather than battling them. Quantum communication is quietly reshaping the foundations of digital trust. Banking, defense, and satellite systems are already testing secure quantum links. Quantum random number generators are entering smartphones and cybersecurity chips. These applications illustrate a profound shift. We are no longer relying on complex mathematical walls to protect secrets. Instead, we enlist the universe itself, uncertainty, entanglement, and the inseparable link between observation and knowledge to safeguard information. Information in the quantum world is no longer just something to be stored or copied. It is inseparable from the system that carries it. When you communicate using quantum states, you are not just sending messages. You are creating correlations between distant parts of the universe. Every photon, every entangled pair, every flicker of uncertainty carries a message that cannot be forged or intercepted. In this quiet shimmer between sender and receiver lies one of the most extraordinary truths of all. Information, like everything else in the quantum world, doesn't just travel, it connects. And as we contemplate these advancements, we are reminded that while quantum mechanics equips us with unprecedented precision and security, it still leaves room for awe. The universe allows multiple interpretations, multiple lenses through which we can understand it. Yet no matter how we view it, the equations predict outcomes flawlessly. We have learned to navigate this strange, layered reality. We use it to protect our data, to explore the cosmos, and to unlock computational power beyond classical imagination. The quantum world whispers its secrets, and we are only beginning to understand how to listen. As we move deeper into the quantum realm, we step beyond practical applications and into the philosophical wonder of what reality truly is. Quantum mechanics works flawlessly. It predicts atomic behavior, lasers, stars, and digital systems with precision. But the meaning behind the equations remains elusive. How can the universe follow such strange rules? And what do these rules say about the world when we are not observing it? Over the decades, physicists and philosophers have proposed numerous interpretations to make sense of the underlying reality. The Copenhagen interpretation, shaped by Niels Bohr and Werner Heisenberg in the 1920s, was one of the first dominant frameworks. According to it, quantum mechanics doesn't describe an objective world independent of observation. It describes the outcomes of measurements, the interface between observer and system. The wave function, a mathematical object encoding all possible states of a particle, is not a physical wave in space. Instead, it is a catalog of possibilities. When a measurement occurs, one possibility becomes reality. and the wave function collapses to reflect that outcome. Bohr's perspective argued that asking what happens inside an atom when unobserved is meaningless. Quantum mechanics tells us only what we can know about nature. Not nature itself. Einstein famously resisted this idea, questioning whether the moon exists when no one is looking. Dissatisfaction with the Copenhagen interpretation led to alternative frameworks. One of the most radical is Hugh Everett's many worlds interpretation, proposed in 1957. Everett refused to introduce collapse as a separate rule, asserting that the wave function never collapses. Instead, all possible outcomes happen simultaneously, each in its own branch of reality. A particle landing left in one universe, right in another. Schrödinger's cat alive in one world, dead in another. We perceive only one branch because our own state becomes entangled with a specific outcome. The many worlds interpretation eliminates randomness entirely. What we see as chance is merely our location within the branching multiverse. This view is elegant, audacious, and unsettling in its scale. Another perspective is the pilot wave theory, also called the de Broglie-Bohm interpretation. It imagines particles always having definite positions guided by a hidden wave. The wave evolves according to Schrödinger's equation, steering particles along deterministic paths that appear random because we cannot perceive the full picture. In this framework, uncertainty is not fundamental, but a reflection of our ignorance. The universe remains orderly, cause and effect intact, yet the wave guiding the particle must be non-local, instantaneously affecting distant particles, a feature Einstein famously described as spooky action at a distance. Pilot wave theory preserves determinism while reproducing all standard quantum predictions, offering a sense of comfort for those uneasy with randomness and observer-dependent reality. Quantum Bayesianism, or QBism, takes a profoundly personal approach. It treats the wave function not as a description of an external reality, but as a representation of an observer's beliefs and expectations about possible outcomes. In this interpretation, quantum mechanics becomes a user's manual for rational decision-making in a world of uncertainty. Measurement outcomes are personal experiences rather than objective facts. Each observer navigates probabilities, updating beliefs with each interaction. The quantum world, from this perspective, is less a map of reality and more a guide for living within it. Beyond these, countless interpretations exist. Objective collapse models that postulate physical mechanisms for wave function collapse, relational interpretations that define quantum states only between interacting systems, and even information-centric views suggesting the universe itself is a vast quantum computer. Each framework addresses the same core questions differently. What does the wave function represent? When, if ever, does it stop being a wave of probabilities and become a single reality? Yet here is the most remarkable fact. Regardless of interpretation, the predictions of quantum mechanics are identical. Parallel universes, hidden guiding waves, subjective probabilities, they all converge on the same experimental outcomes. Photons, electrons, and atoms behave consistently. The mathematics is unchanging. It doesn't matter which philosophical lens we apply. This unity amid conceptual diversity demonstrates a profound truth. Quantum mechanics is a language we have learned to speak fluently, even if the meaning behind the words remains mysterious. In this sense, the universe permits multiple ways of understanding, multiple narratives coexisting, all consistent with observable reality. The equations provide rhythm and structure, but the interpretation, the story we tell ourselves, is shaped by our curiosity, our imagination, and our comfort with uncertainty. Perhaps this multiplicity of views is itself a lesson. Understanding isn't merely about finding answers, It is about learning to coexist with questions. The beauty of quantum mechanics lies not just in its predictive power, but in the philosophical freedom it grants. It challenges assumptions, reframes causality, and invites us to contemplate infinity, uncertainty, and the extraordinary tapestry of reality. We have seen how these ideas influence secure communication, distributed computing, and random number generation, but they also transform our perception of the world. Each photon, each entangled particle, each superposition is a window into a universe far richer and more layered than our classical intuition allows. As we continue this journey, it is clear that quantum mechanics is more than a set of equations. It is a framework for exploring possibility, a mirror reflecting our desire for understanding, and a guide for navigating a reality that refuses to be fully tamed. As we move forward, we return from the philosophical to the practical, exploring how the strange rules of quantum mechanics are reshaping the way we handle information. Quantum communication, built on the very foundations of uncertainty and entanglement, promises to revolutionize the security and efficiency of our networks. Unlike classical encryption, which relies on mathematical difficulty, quantum communication leverages the laws of physics themselves to guarantee secrecy. One of the most powerful tools in this domain is quantum key distribution, or QKD. In classical cryptography, two parties share a secret key to encrypt messages. The challenge has always been transmitting that key securely. QKD solves this by encoding the key into quantum states, typically photons with distinct polarizations. The laws of quantum mechanics make eavesdropping detectable. Any attempt to measure these photons disturbs them, leaving observable traces. If the sender and receiver detect anomalies beyond expected noise, they know someone has tried to intercept the key. Here, physics itself acts as the bodyguard of information, not algorithms. Building on these principles, quantum teleportation allows the transfer of a particle's quantum state from one location to another without physically moving the particle itself. It begins with an entangled pair of particles, A and B. Particle A remains with the sender. Particle B travels to the receiver. The sender then performs a joint measurement on particle A and the system whose state they wish to transmit. This measurement destroys the original state, but generates classical data that, when sent to the receiver, allows particle B to assume the exact state of the original. No faster-than-light signaling occurs, no particles are cloned, the quantum information itself has been teleported. This process has profound implications. Teleportation could allow distributed quantum computers to share states instantaneously or enable secure quantum networks where information exists only in transit, never in a vulnerable form. Alongside teleportation, true quantum randomness plays a critical role. Unlike classical random number generators, which are ultimately predictable if the system is understood, quantum processes offer fundamentally unpredictable outcomes. Photons passing through polarizing beam splitters or other quantum mechanisms generate sequences of bits that cannot be anticipated, forming the backbone of quantum encryption, simulations, and secure communications. Yet even the most promising quantum technologies face hurdles. Quantum states are fragile. Entanglement and coherence degrade over distance. Unlike classical signals, which can be amplified, quantum signals cannot be copied or boosted without disruption. This is where quantum repeaters come into play. By linking entangled pairs across short network segments and performing entanglement swapping, these devices can extend quantum networks over city-scale or even continental distances. Quantum memories store particles temporarily, coordinating their states across nodes without direct measurement. In combination with satellites and ground stations, this approach lays the foundation for a global quantum internet, a network that is secure, ultra-precise, and capable of distributed computation. The impact of quantum communication extends beyond security. It forces a reconsideration of what information truly is. In classical physics, information is freely copied, stored, and transmitted. In quantum mechanics, information is inseparable from the system carrying it. Each act of communication creates a correlation, a connection that cannot be reproduced or intercepted without detection. Quantum mechanics transforms communication from a mere transmission of data into the extension of correlations across space. Already, these technologies are being integrated into practical applications. Quantum secure banking and defense networks are being tested. Quantum random number generators find their way into smartphones and cybersecurity chips. Though largely invisible to the everyday user, these innovations quietly redefine the standards of trust, security, and computation. They remind us that fragility and uncertainty, once considered obstacles, can become the very tools that safeguard our information. The narrative of quantum information is one of paradoxical elegance. We turned unpredictability into security, fragility into a feature, and the elusive behavior of the quantum world into the foundation of modern technology. As we look to the horizon of quantum networks, teleportation, and entangled systems, we are reminded that the universe itself sets the rules, and by respecting these rules, we can harness them to create systems more secure, more interconnected, and more extraordinary than anything classical physics could allow. The strange, subtle dance of entanglement, coherence, and uncertainty is no longer a theoretical curiosity. It is the infrastructure of tomorrow's quantum world. As we venture further into the quantum world, the focus shifts from practical applications to the profound philosophical questions that have haunted physicists for over a century. Quantum mechanics is not just a toolkit for predicting outcomes. It is a lens through which the nature of reality itself is questioned. Every particle, every photon, every superposition invites us to reconsider what it means to exist, to measure and to know. In the early 20th century, the Copenhagen interpretation became the dominant view. Spearheaded by Niels Bohr and Werner Heisenberg, it emphasized that quantum mechanics does not describe an independent objective reality. Instead, it tells us about measurement outcomes, the interface between observer and system. The wave function, a mathematical object encoding all possible states of a particle, is not a physical wave, but a catalog of potentialities. When a measurement occurs, the wave function collapses, selecting one outcome from many. Bohr argued that asking what happens inside an atom when unobserved is meaningless. Quantum mechanics, in this view, only provides information about what can be known, not about what exists independently. Einstein, famously uneasy with this approach, resisted the idea that the universe depends on observation to exist. "Do you really believe the moon isn't there when you're not looking at it?" he asked, highlighting the discomfort many feel with observer-dependent reality. Dissatisfaction with the Copenhagen stance inspired alternative interpretations, each attempting to reconcile quantum mechanics with a more intuitive understanding of reality. The many worlds interpretation, proposed by Hugh Everett in 1957, eliminates the collapse entirely. Instead, the wave function evolves deterministically, and every possible outcome occurs in its own branching universe. Each measurement splits reality. In one branch, a particle lands on the left, in another, it lands on the right. Schrödinger's cat is alive in one world and dead in another. Observers become entangled with outcomes, perceiving only a single thread, while countless parallel realities persist unseen. In this framework, randomness is illusory. Chance is replaced by our position within an ever-branching multiverse. Another alternative, the pilot wave theory or de Broglie-Bohm interpretation, posits that particles always have definite positions guided by a hidden wave. This wave evolves according to Schrödinger's equation, steering particles along deterministic paths that appear random only because observers lack full knowledge. Uncertainty arises not from inherent indeterminacy, but from ignorance. The universe remains orderly, and the observer's role is simply to uncover pre-existing conditions. Yet, pilot wave theory introduces non-locality. The guiding wave can influence particles instantaneously across vast distances, echoing the spooky action at a distance that Einstein found troubling but that quantum experiments confirm. Then there's QBism, or quantum Bayesianism, which reframes quantum mechanics entirely. Here, the wave function is not an external reality, but a reflection of the observer's personal beliefs about possible outcomes. Probabilities are tools for navigating uncertainty, and measurement outcomes are personal experiences rather than objective truths. QBism sidesteps debates over collapse or hidden variables, treating quantum mechanics as a user's manual for rational decision-making in an unpredictable world. Beyond these, a host of other interpretations continue to explore objective collapse models, relational perspectives, and even universe as quantum computer views. Each addresses the same fundamental questions. What does the wave function represent? When, if ever, does a quantum system settle into a single reality? How do observers influence outcomes? Remarkably, despite divergent stories, all interpretations yield identical experimental predictions. Whether one envisions parallel universes, hidden guiding waves, or subjective probabilities, photons, electrons, and atoms behave consistently. The mathematics of quantum mechanics remains flawless, indifferent to the narrative we attach to it. This demonstrates the duality of quantum theory. Its predictive power is absolute, yet its interpretation is fluid. In navigating these interpretations, we confront both humility and wonder. The universe allows multiple ways of understanding, suggesting that its truth may be deeper than any single narrative can capture. Mathematics provides the rhythm of reality, but meaning, the story we tell ourselves about that rhythm, is open to perspective. Perhaps in embracing this ambiguity, we grasp the quiet beauty of quantum mechanics. It does not hand us certainty, but mystery shaped with precision. Each interpretation mirrors aspects of our cognition, our desire for order, our tolerance for ambiguity, our comfort with infinity. The equations remain unchanged, the predictions unaltered, yet the stories we construct reveal as much about ourselves as about the universe. As we reflect on these layers of possibility, we see that observation does more than measure. It participates. Every interaction, every quantum choice gently brings one version of reality into focus, highlighting the intimate connection between observer and observed. The quantum world, in its infinite subtlety, reminds us that understanding is not merely about answers. It is about living gracefully with questions and appreciating the profound interplay of chance, certainty, and perception. Having explored the interpretations of quantum mechanics, we now return to its practical and philosophical implications. Quantum theory is not just a playground for thought experiments. It is transforming the way we communicate, compute, and understand reality itself. Quantum communication leverages the very principles we have explored: uncertainty, entanglement, and superposition to achieve feats once thought impossible. Unlike classical systems where encryption relies on computational complexity, quantum communication uses the laws of physics to guarantee privacy. Every attempt to eavesdrop on a quantum message leaves detectable traces. Photons entangled across distances form unbreakable bonds. The very act of measurement ensures that any interception can be detected. Quantum key distribution, QKD, has already moved from theory to practice. Cities like Beijing, Vienna, and Geneva now operate quantum-secure networks, and in 2017, China's satellite demonstrated entanglement over thousands of kilometers, linking ground stations securely through space. Quantum teleportation, too, has progressed from tabletop experiments to satellites, enabling the transfer of quantum states without moving the particles themselves. These advancements hint at a future quantum internet, where communication, computation, and synchronization intertwine seamlessly. Yet, quantum systems remain fragile. Entanglement is easily disrupted, and quantum states cannot be copied like classical signals. This has led to innovations such as quantum repeaters, which extend entanglement across long distances, forming the backbone of global quantum networks. Step by step, segment by segment, distant nodes are linked, creating a coherent system that respects the very laws that govern the universe. At its core, quantum communication turns supposed weaknesses into strengths. The fragility of quantum states protects data. Inherent randomness ensures unpredictability. Entanglement enforces security. Every constraint becomes a feature, every limitation a safeguard. Beyond encryption, it challenges our understanding of information itself. Information in a quantum context is inseparable from the system that carries it. It is as tangible as mass or energy. Sending quantum information is not merely transmission. It is weaving correlations across space, creating connections that are fundamentally inseparable. The practical applications are already reshaping our world. Quantum-secure networks are tested in banking, defense, and satellite communications. Quantum random number generators are embedded in cybersecurity hardware and even mobile devices. These technologies, though invisible to most, are quietly redefining trust, privacy, and computation in the digital age. At the same time, quantum mechanics continues to challenge our philosophical intuition. What is reality when every measurement seems to create the very thing it observes? Interpretations from Copenhagen to many worlds, pilot waves to QBism, illustrate the richness of quantum thought. The predictions remain consistent, yet our understanding of existence is layered with possibilities. In one sense, every interpretation is a lens through which we glimpse different facets of the same reality, reflecting not just the universe, but our own ways of engaging with it. Perhaps the most profound lesson of quantum mechanics is humility. The universe is stranger and more intricate than our language or imagination can fully capture. Measurement is not passive. Observation is participation. Every photon, every entangled particle, every ripple of probability carries information that shapes the way reality unfolds. The future of science and communication rests not just on what we can calculate, but on how we embrace uncertainty, harness entanglement, and appreciate the delicate dance between knowledge and mystery. As we look ahead, the possibilities are breathtaking. Distributed quantum computers could share states instantaneously. Quantum networks could secure global communications, and fundamental experiments may reveal even deeper truths about the fabric of the cosmos. Yet, the underlying lesson remains simple. By aligning technology with the fundamental laws of nature, we create systems that are both powerful and harmonious, a testament to the elegance of the universe itself. Quantum mechanics does not just describe the world, it transforms it. From the infinitesimal behavior of photons to the global networks of tomorrow, from philosophical dilemmas to practical security, the quantum revolution is underway. And as we stand at its frontier, we are reminded that in the quantum world, to know is to participate, to observe is to connect, and to explore is to expand not just our understanding, but the very possibilities of reality itself. And so, our quiet voyage through the quantum world reaches its gentle conclusion. Over the past hours, we have wandered through the strange landscapes of uncertainty, entanglement, and probability. We have glimpsed a universe that refuses to be pinned down, that hums with possibility, and that weaves connection into the very fabric of reality, from the tiniest photon dancing unpredictably through a polarizing beam splitter, to the entangled pairs bridging continents and satellites. We have seen how the universe whispers its secrets in ways that are both precise and elusive. Quantum mechanics does not shout its truths. It hums them softly, inviting patience, curiosity, and wonder. And in listening carefully, in letting ourselves drift alongside these invisible threads, we begin to sense a deeper harmony, one that turns the fragility of particles into the strength of information, and the uncertainty of outcomes into the certainty of beauty. Every experiment we explored, every interpretation we touched, from Copenhagen to many worlds, pilot waves to QBism, offers a lens into the same mysterious world. Each lens reflects a different shade of understanding, reminding us that reality is as much about perspective as it is about particles. The universe is not just something we observe. It is something we participate in, something we connect with, moment by moment, measurement by measurement. And as these quantum truths ripple outward, they are quietly transforming our everyday lives. Banks and satellites, smartphones and servers all now carry the echoes of entanglement and randomness, reshaping trust and security. Even if these mechanisms remain invisible to most, their influence is profound. The future is being built not by brute force alone, but by harmony with the very laws that govern existence. So, take a moment to sit with this realization. In the quantum realm, every observation matters. Every choice, every measurement, every flicker of light carries significance. The universe does not simply happen. It unfolds in collaboration with those who witness it. And in that collaboration lies both responsibility and awe, a reminder that curiosity is not just a pursuit of knowledge, but a delicate, ongoing conversation with reality itself. Thank you for drifting through these 101 quantum truths with me tonight. Your presence, your attention, your quiet wonder, it all contributes to this shared journey. If you found your mind expanded or your imagination stirred, a like goes a long way in helping this peaceful exploration reach other curious minds. And if you are new here, subscribing to the Wonder Lab ensures that more calm, thoughtful adventures await wherever your curiosity leads. For those already part of this gentle community, thank you. Your engagement, your comments, your questions, these are the sparks that keep the exploration alive. Leave a thought, a suggestion, or a wonder in the comments, and together we will continue to drift through the cosmos of knowledge, one mindful step at a time. Until next time, may your thoughts settle like starlight on quiet waters. May your curiosity remain luminous, and may your nights be full of the gentle, expansive mystery that is the quantum world. For in the end, the universe is not just out there. It is within you, within every observation, and within every act of discovery. And that perhaps is the most extraordinary truth of all.